Yes. You will. You will. Yeah. Yes. Okay. So if you recall, logistic growth is the exponential growth equation, which is the maximum rate of increase multiplied by the population size, and that's under idealized situations. Logistic growth, remember, is when you're not under idealized situations, so therefore you have limited resources and so on, so that there is a carrying capacity. And so this part of the equation, remember, factors in how close your population size is to K. So there's your carrying capacity. If N, your population size, is really, really low, so you know, compared to K. So K is up here, let's say it's 1,000, your population size is 50. So you've got a big difference between your carrying capacity and what your population size is. What would this number be like? So if K is very high compared to N, what would this top number look like? K is very high to compared to N. N is very low. If you took K minus N and divided by K, be very close to 1, all right? Because this is going to be so small that when you subtract it, it's going to be like K, almost K divided by K. So it's close to 1. And so therefore, if that's the case, if your population size is really small, and then that means this is going to be close to 1, that means that the population is really going to grow almost exponentially at its maximum rate. And that makes sense because N is really small, so you have a lot of room to grow, a lot of resources, a lot of space, and so on. So then what happens is that as it begins to grow and N becomes closer and closer to K, what happens to this number? N gets closer and closer to 0, right? It's going to get smaller and smaller and smaller because K minus N, this number is going to get smaller. And then you divide this out. So it's going to be some decimal, all right, getting closer from 1 going down, closer to the carrying capacity. So what would happen to the overall rate of growth as N gets closer? It's going to go down. It's going to slow down. And then when the population reaches carrying capacity, what does it do to this number? So N now reaches K. So N and K are the same number. 0, right? Because this is going to be 0. We divide it out, it's going to be 0. Multiplied by this, it's going to be 0. So that makes sense. When you reach to the carrying capacity, it's not going to grow anything. Which is what this next slide, these 3 bullets are about. So when N is small compared to K, we have that portion of the equation close to 1. And we get close to the maximum rate of increase. Then when N becomes larger, and as it approaches K, as it large compared to K, then that part of the equation is close to 0, and the rate of increase is small. And then, of course, when N equals K, the population stops growing. We'll come back and look at this chart in just a second here. I want to do a couple of other bullets here first and look at. So when we have a population that is growing logistically and graph out the population, it looks like an S-shaped curve. S is the stands for sigmoid. Exponential growth looked like what? J-shaped curve, right? So the new individuals are added to the population most rapidly at intermediate population sizes. So not really small and not really big, so kind of in between there. And then as the population size approaches K, the population growth rate decreases as N approaches K. And that's what we see in this graph here. So this has the 2 models of population growth. So remember, so this is the change in the population size over the change in time. And so this right here, 1, that's our max. So remember, exponential growth is R max times n. And it looks like this, a J-shaped curve. Now, I'm comparing the population that's growing exponentially versus logistically. And so here, again, it's still, R max is the same, 1. Except, so this part of the equation is the same as exponential growth, but remember this is taking into account carrying capacity, which is represented by this dotted line, which is 1,500. And even if that dotted line wasn't there, you'd be able to tell the carrying capacity where it was at, because it's where what happens? It levels off, all right? So you would be able to tell that if you weren't given that based upon this graph. All right, and so this is the K minus N divided by K part of the equation. And so that's what we see here. And so very early on, you get a slower growth rate, and then in the middle here, you get your maximum growth rate, which is a steeper curve. And then as you approach carrying capacity, it starts to level off because, as we just talked about, as N increases, it gets closer and closer to 1,500, which lowers that rate, and therefore levels off. And so it slows down there. All right. So now let's go back to that chart here. So this chart here shows some calculations of a population. It says here, logistic growth of a hypothetical population, and tells you the carrying capacity. So to use these equations for logistic growth, R max N, K minus N divided by K, to use this, you need to know some information about the population. So the first thing you need to know is what the carrying capacity is. You need to know what the starting size of the population is, so that's what this is here, so that's N, and the rate of increase. And so here they give you that, so this is the rate of increase of 1 we're using. So when the population, when this hypothetical population, when it's 25 and the rate of increase is 1, it's kind of going step by step. This is the overall equation at the end. And it's going step by step how to do this. So to get K minus N, so they typed in their calculator 1,500 minus N, which is 25, and divided by K, which is 1,500. Notice here, 1,500 and the N is 25. 1,525, that's a huge difference. 25 is really small compared to K. So therefore, as we just wrote, it's close to 1, so it's 0.98, and so that makes sense here. And so then we add in the rate. Well, the rate in this example happens to be 1, so it will be the same there. And now we add in the population size to figure out how much it's going to grow by. And so this is the rate, and then if the population is 25, we plug that in here, and we get a growth of 25 new individuals. And so then we let that population grow, and then look at it when it's 100 and do the same thing. And when it grows up and is eventually 250 and so on and so forth, and we can look at the rate and so on. So what I want you to do is take this and apply it to the chart that I gave you yesterday. So you have different population sizes and different rates of increase, and what I'd like you to do is just practice using the formula. So this also is logistic growth.
get for this one? Yeah, she got 0.9. Yeah.
Confused on that. Yeah, I'm confused because this, don't we just do like this?
Yeah, then it's 0.9.
But I mean, the fact that you got one makes sense. Whole numbers. What is that?
9. My calculator. We had to do the scavenger hunt for math, and he got another signature. It's a pop socket. And it helps you really pump.
It's like
It helps you so you don't
it's
also,
also
yes.
and it's so much.
It's $10 on line. Like on pop socket, on .com. So nice. She advertises it.
Yeah, she does.
I tweeted them.
Yeah, they tweeted her back too. They said they come out to Colorado.
That's funny. I like that.
She's collecting everybody that buys one because of her. I was one of them.
So many kids' grandma got one.
I like how grandma got one. Grandma usually called me
When you're done, what I'd like you to do is, this was logistic growth. So what I'd like you to do is make a column on the right-hand side, and we're gonna do, maybe do a calculation for the same population. So the population size, those first two columns are still true, but I want you to calculate the change in growth if the population is growing exponentially. So you're going to label this column exponential growth. The last column there was logistic growth, taking into carrying capacity. And so now if that same population it has unlimited resources and unlimited space, what would the growth look like and how would it be different? So the first thing you need to do is figure out what's the equation you're going to use if the population is growing exponentially.
Okay. So you want to tell me what it is? Yeah, I feel like you're fine.
Yeah, we did.
Okay.
I hope so.
So you look under exponential growth.
Oh, I found it.
It's funny that way.
How it works out like that.
Okay, so it's still D and what? It's 5. It's R. It's these two.
It's the maximum growth rate.
It's this times this.
What's
1,000
minus 1,000 divided by 6?
What? What did you just say to me?
Oh, is this wrong? I think I didn't type it in my head, so this whole column is probably wrong.
Wow, thanks. The whole row.
That's what I meant.
What is
But
it?
you
Can
gave
you tell
1,000
me what they
minus
are?
1,000 divided by 1,000. So all
Okay, wait, so what is the actual equation? Is it R max times N?
Yeah. But it's the Oh, yeah, you do.
I don't,
What was
I don't get the D and
Yeah, and these are just about something. What do you get if you just do?
oh my god,
Okay, but you were about to say that was your own.
oh really? You're
That's actually okay. I'm just gonna record.
oh my
Yeah, I know what it is.
okay, well you don't even need a How did you do it?
I just did
What I did?
But I mean, that's innate. I'm not sure. Don't write it down. 0.05 times 10, yeah. Don't write it down.
But isn't it the R max? Oh no.
I told you not to.
I'm just writing it on the side.
No, I think you're right. That's because that's what we all know.
Oh my god. Blow me
But the thing is, you don't accept it. There's enough balance. If you repeat it too much, then you're not. If you repeat it too much, yeah, then you'll be. I've had that experience. But usually there's G's to my.
So let's look at this.
You did it right. You did it. Alright, so.
So here you have, for the logistic growth, you have, you should have 0.98, 4.5, come on up, 9.4, 12.5, 9.40. And that's logistic growth. So remember, logistic growth is you have the highest rate in the intermediate. So therefore, around 500, you get the greatest increase in individuals in the population. Even though it's not the fastest rate, but in combination between the number of individuals at that time and the relatively high rate, you get the highest individuals added to the population at that particular time, because there's just more individuals. And so in looking at this, you can see that it increases to a point at 12.5, and then as that population at 500 starts to approach your carrying capacity at 1,000, starts to then decrease, and you can see the rate decreasing here until eventually the rate is 0 and no new individuals are added because the population is 1,000 and has reached the carrying capacity. So this would be the leveling off portion of the S-shaped curve. All right. So that's if there are limited resources. So then I had you do exponential growth, And these are the numbers you should have gotten, so 1, 5, 12.5, 25, 37.5, and 50. So this is, you're just using R max N was the calculation, and so you're not taking into account carrying capacity at all, because if exponential growth is occurring, you don't have a carrying capacity, you have an idealized situation, and so therefore it makes sense that the population would continue to grow at its maximum rate, and so you don't see a leveling off here, and if you were to graph this, it would look like a J-shaped curve. All right, and so that shows you the differences there and gives you practice using the calculation. All right, so now let's go back. So I'm going to give you a couple examples, real life examples of logistic models. One is Paramecia, are little one-celled organisms that live in fresh water, so lakes and so on, ponds. If you take some Paramecia and grow them in the laboratory, eventually their growth pattern will fit an S-shaped curve. And so at first they'll grow and reproduce pretty rapidly at first, because if they're in the lab and have this constant environment, they don't have any natural predators because you've taken that away. There's not a lot of competition right away because there's space in the water that you give them. You're giving them food and so on. So they begin to reproduce. But eventually, unless you keep enlarging the tank or the amount of water that they're in, eventually as they reproduce, they'll start the resources become limited in a constant environment, assuming that you're giving them the same amount of food, the tank stays the same, and so on. And so their growth looks like this. So this is your days and time. This is the number of paramecium per milliliter of water. So they took a milliliter of water and counted the paramecium, and so that's how they got the data here. And so they made the best shaped curve here based upon the data, which is the dots on here. And so this is the actual data they collected and then made this S-shaped curve. And so roughly the paramecium in this laboratory experiment, carrying capacity is roughly what? If you had to estimate carrying capacity here. Yeah, about 900, right? Paramecium per milliliter, all right? And so that's that. And that type of question, sometimes, remember you have the math part of the AP test, sometimes it's as simple as that. Like they'll give you a graph and like have you calculate this, so, and estimate, all right? So sometimes it's not as simple as that, but sometimes it is. So that's the carrying capacity. Notice here, this is a Daphnia. Daphnia are multicellular. You can see them with your naked eye. They're still pretty small. They also live in fresh water. A lot of people in layman's terms will call them a water flea. And so they live in the same environment as the paramecium. And if you do a similar experiment with these guys, notice here also the S-shaped curve, but I want to show you here this little cluster right here that has happened, and they haven't included that in the curve because we're looking at overall growth. And so a lot of organisms, when they're growing in this part here, before they reach carrying capacity, what they call overshoot the carrying capacity. So this would be like they're reproducing and then they reproduce too much, and then there's not enough resources, and then some of them die back off. All right, and so then it starts to fluctuate right around that carrying capacity. And so that's the Daphnia. So the next bullet there is that some populations overshoot K, the carrying capacity, before settling down to that stable density, fluctuating right around carrying capacity. All right, so those are the two different types of growth. Now we're going to look at some characteristics of different populations and kind of strategies that they have and characteristics that affect growth. And they're called life history traits. Organisms' life history comprises the traits that affect its schedule of reproduction as well as its survival. So we're going to look at reproduction first and then survival.
Is it supposed to be a concept to do with 200?
Yes, yes. I adapted to from the new textbook. I changed my years, but so life history traits, evolutionary outcomes. We're going to look at things like development, organization, physiology, and behavior. And so when we talk about life history and things that affect growth about a population, there's three main things that can affect growth that are important. The first one is for the particular population of species, the age at which reproduction begins. Different populations begin reproduction at different times. So some populations, the organisms reproduce within the year that they're born. Some reproduce after 20 years, and so on. So the age at which reproduction begins can affect the rate at which a population grows. For instance, if you have a young, if we have a young age at which reproduction begins to occur in a population, would that increase or decrease the growth rate? Yeah, increase. It probably would if they start having children at an earlier age. Another piece of information that might be helpful is not only when they begin to reproduce, but how often they reproduce as well. So how often the reproduction occurs. So for instance, if the organisms reproduce early, but they only reproduce once, versus an organism that reproduces a little bit later but reproduces frequently, that can play a difference in how the population grows. And the last thing that can play a difference is when they reproduce, how many kids do they have, all right? And so how many offspring are produced per reproductive episode. So like, salmon are born in a river and they swim to the ocean, and where they grow a couple years, and then the females go back to that same river where they're born, and they lay thousands of eggs in the river, and then they die. All right, and so that's the only time that they reproduce. So therefore, you have to take into account they reproduce once, how many eggs do so all of that plays a role in population growth, and especially comparing different species and so on. So when we look at trade-offs, meaning that there are some things that an organism gives up in survival and reproduction. So organisms have finite resources, which may lead to trade-offs between survival and reproduction. So we have this delicate balance where in order for the population to stay alive or stay around, you have to reproduce and replace yourself and have kids and so on and so forth. But the more kids that you have, the less resources that there are, and so there's this balance of act between the two. So, for example, there's a trade-off between survival and paternal care in European kestrels. European kestrels are birds. Paternal care is the care with the father, right? This is what the kestrel looks like here. And so that what they were looking at is they did a study with, it says down here brood size. So it says reduced brood size, normal brood size, and large brood size. This is the number of eggs that they have. So in the experiment, what they did is, so the normal brood size is 5 to 6 eggs. So what they did in this experiment is they took some of the normal brood size eggs, so they have different couples, kind of birds, all right, in their nests, and they took, in some of them, they took some of the eggs away, which then reduced the brood size, so they took a couple of them. And then in some of the nests, they took the ones that they took away and added them to other nests, so the other nests were bigger. And then they watched and waited to see what happened, and they were studying the relationship between reproduction and the number of offspring that you have and the parental survivorship. And so if we look here, this is the mom and the dad, all right, of each one of these organisms in the nest. And then this is what they measure is the parent surviving the following winter. And so this is in percentages. So, so what is the relationship between brood size and survivorship based upon this curve? Nathan?
The larger the brood size, the less likely that either parents are surviving.
That's right. The larger the brood size, the less likely that either parent, they both go down in terms of that for the next winter. And so there's a negative effect on brood size when the brood size is organism when the brood size is large. Why might that be? Okay, so more out of their body to actually produce the eggs.
So if there's more like babies, then they need more resources, so the parents might just like die off to get more resources.
Okay, yeah, absolutely. All right, and so, so that's what we see here. So there's a trade-off here. So this is the normal brood size. So we see here, so there's a trade-off between normal brood size. If they had even a less brood size, there's a better survivorship rate, according to this. But this is the normal brood size in the wild. So this is what we're talking about with a trade-off, where they have to have a certain number of individuals to replenish the population, and the trade-off is that the parents have a decreased survivorship. And so there's that balance between those. And that's the close-up here. Talk about plants here. Plants, some produce a large number of small seeds. I talked about this yesterday, ensuring that at least some of them will grow and eventually reproduce. So I used the example of a maple tree yesterday with all the little helicopters. A dandelion could be the same way. They produce lots of little seeds on those. And so they produce large numbers, so they're taking energy to produce large numbers, but that ensures that some will grow and the population will continue on. So that's one strategy. This is a picture of the dandelion seeds. And so then I'm going to talk here next about the Brazil nut. This is the picture of the Brazil nut tree. The Brazil nut is a bigger seed than the dandelion seeds. So other plants like the Brazil nut tree produce moderate numbers of larger seeds. So, and what they do is the seeds provide a large store of energy that will help the seedlings to become established. So in this strategy, you are producing less seeds, but you have a lot of energy. Remember, a seed contains a baby plant, and baby plants are in a dormant stage until conditions are right, like the temperature and enough water and so on to stimulate growth. But the baby seed, when the baby plant inside the seed starts to grow, it can't do photosynthesis to get energy, to make glucose, so it uses energy stored up in the seed for that. And so therefore this plant is the parent plant is spending energy to put lots of energy storage in the seeds so that the seeds that they do produce have a more likely chance of surviving. So in describing populations, there's K and R selection. K stands for carrying capacity. This is density-dependent selection. Selects for life history traits, so those things about reproduction and survival and so on that are sensitive to population density. So populations like this are usually close to the carrying capacity. Close to. Okay. So, like for example, they call what's called an old growth forest, but a forest that's been around for a long time. You've got trees, very big trees that have been around for hundreds of years and so on. And so it's pretty established. There's really not a lot of room for additions, and so it's very close to carrying capacity. And so that's called K selection. R selection, or density independent, means that it says selects life history traits that maximize reproduction. Density independent means that it's independent of the density or crowdedness. So these are usually populations that are far from. Okay. So like in real life, it would be like if a farmer had 10 acres of land and they decided I'm done farming, I'm gonna retire, and they just stopped cultivating the land. So you have this whole empty field, and for like a species of weeds, they would be able to grow exponentially there. And so that would be an example of a population that really is density independent. So when we look at factors that affect population growth, we clump them into two categories, what are called density independent factors and density dependent factors. So density independent factors, any factor limiting the population of the size of the population, that the effect is not dependent on the number of individuals in the population. So an example would be an earthquake. An earthquake hits, members of the population are killed. The earthquake affects that population the same whether or not that population is really dense and crowded or if it's not. And so that's why it's density independent. Can somebody think of another density independent factor? Another density independent factor. The effect is not dependent on the number of individuals in the population. Roman? I can't hear. A hurricane? Okay, yeah, a hurricane. Would be an example of that. Anybody else? Anybody wants to volunteer? Huh? A tsunami. What do all these? Diseases. Would density play a role? Do you think? Yeah. With a disease, if a population is more dense, how's that going to affect the population? It's going to spread a lot quicker if they're close together versus if they're far apart. It won't most likely affect it as much because if the organisms never come into contact with each other and one organism has a disease, it might just affect that organism and not the rest of the population. So all of the examples that you guys just talked about here really are kind of natural disasters or weather-related conditions, and so that's usually the case with density-independent factors. So density-dependent factors, on the other hand, is any factor that limits the size of the population that the effect is dependent on the number of individuals. And by coincidence, I use the example of disease. So disease will have a greater effect in limiting the growth of a large population or more dense population, since overcrowding facilitates its spread. Anybody think of another density-dependent factor?
Like hunting or predators.
Hunting or predator, so elaborate on that.
So like if there's more organisms that are being like it's a greater chance for a predator to get one if there's a lot of them.
Yeah, absolutely.
Well, like in food, like it's more scarce. Like some like food they usually eat isn't around anymore because they don't. Like, the food the plant doesn't come from like died off. Then like the more people, the more like that the population is, the more people are gonna have less food.
Okay, yeah. Somebody in the room is over here. Change your mind. Oh, okay. All right. So let's look at population change and population density. And density-independent populations, not dependent upon the density. Birth rate and death rate do not change with population density. Most populations we look at are density-dependent populations where the birth rates will fall and death rates rise with population density. So as it becomes more dense, the less individuals are born and more individuals die. And so we're going to take a look and focus on here on density dependent. So density dependent birth and death rates are affected by many factors such as, so competition for resources, which is what I think you were getting at there. Territoriality, so it'll talk about animals that mark their territory that decreases the density. Disease we've talked about, predation is what Nathan said, and then toxic waste. And a lot of these are pretty self-explanatory, but I just have a little slide for each one of them here. So competition for resources, how that's density dependent. Increasing population density intensifies competition for resources and therefore results in a lower birth rate and usually maybe a higher death rate. Disease, we've already talked about that. Population density can influence the health and survival of organisms. In dense populations, pathogens, disease-causing organisms can spread more rapidly between the individuals versus if they're less dense, like I said earlier, they won't come into contact with each other and won't spread. Predation, which is what Lucas talked about here, as the prey population builds up, and so that becomes dense, predators may start to feed preferentially on that species, because if you have choices as a predator and you have an unlimited supply of a certain prey and it's easy to get, that's what you'll feed off of. Territoriality, competition for territory may limit the density. So because organisms mark their territory, keeping the other organisms away, and therefore causing and decreasing the density. And there's the cheetah marking his territory. And then toxic waste. Toxic waste, it says accumulation of toxic waste can contribute to density-dependent regulation of population size. So what do I mean by accumulation of toxic waste? What would that be in the wild? Accumulation of toxic waste. Nathan? Okay, yeah, pollution, like for us. All right, we put pollution in. What about an animal? All right, their feces, maybe. Okay, so they're solid waste. And you have obviously more of that when you have a higher density. So, and so this last little bit here is about how populations affect one another, the dynamics, focuses on the complex interactions between biotic and abiotic factors. Biotic means living, abiotic means non-living. So we're going to look at how they can, both of those can affect a population and therefore cause variation and changes in population size. So they've done a lot of long-term population studies with lots of different organisms. And it says they've challenged the hypothesis that populations of large mammals are relatively stable over time, meaning that they don't change. What they found is that some organisms fluctuate, and some of them fluctuate in response to biotic factors, like a predator. Some fluctuate in response to food availability and what the weather was like that year. And then some fluctuate in response to each other. And so both weather and predator population can affect the population size over time. So we'll talk about this. The moose population on Isle Royal collapsed during a harsh winter and when wolf numbers peaked. Isle Royal, where's that at? No. Here in Michigan, it's on the Lake Superior. It's the island of Lake Superior. All right. So we'll talk about that on Monday. I forgot.